Hello, and welcome to Med Math, a look at dimensional analysis for infusion rate calculations. Dimensional analysis is just a fancy term for making sure that units cancel. It's easier than memorizing formulas and less prone to mistakes. Ratios are usually written as fractions or with a colon separating numerator and denominator. The recent switch from ratios for epi and lidocaine caused some confusion, but it was really just a change from using the colon ratio to the actual strength of the drug to minimize confusion, particularly for pediatric dosing. The former ratios refer to the fraction of grams per mil, so 1 to 1,000 is 1 milligram per mil, and 1 to 10,000 is 1/10 of a milligram per mil. To use dimensional analysis, it's important to understand that the strategy for getting from the information you have to the answer you want is to make sure that the units are accounted for on both the top and the bottom of the overall fraction. Once you get used to that, the conversions will kind of reveal themselves. It's important to match the units exactly. You can only eliminate the ones that are on both sides of the fraction line. But as long as the units you want are in the right place with none left over, you will have the right answer. So let's look at our first problem. This is a lot of information with a lot of detractors to wade through before you can figure out what info you actually need. The question we need to answer from the final sentence is the infusion rate. If we remove the noise of the descriptors, we can find the patient weight along with the ordered drug, dose, and concentration. With these three pieces of information, we can start working on the solution. We have a weight of 100 kilograms, weight-based dose of 50 mics per kilo per minute, and propofol concentration of 10 milligrams per mil. Doing it by looking at each individual piece, most folks would start with the patient weight to get the dose needed per unit time. Then the time conversion, then the unit conversion to milligrams. And finally, the concentration of the drug is converted to give the final answer. The problems with doing it this way is 1. Remembering each needed step, 2. Remembering unit conversions, and 3. Not having a defined order and standard process for working this type of problem. Now that we have the answer, let's look at it a different way. By laying out the problem as one big fraction, we can use the info we have in a standard way and track the units. It's easiest to do rate, weight, and concentration in that order. If there are conversions needed as you cancel out units, they can be added to the end of the fraction. For this topic, we'll refer to the numerator and denominator more simply as just the top and the bottom of the fraction. The weight-based dosing rate from the order is 50 mics per kilo per minute. This goes in the first block. It's okay mathematically to have the units fraction of kilograms per minute in the denominator, and we'll treat both units as being eliminated by units in the top of the fraction as we go. The patient weight is placed in the second block on the top so that it'll cancel with the kilograms unit in the denominator. We'll put a 1 in the bottom of that one just as a placeholder. Next comes the concentration. It's 10 milligrams per mil, but we know that we want our final answer to be in mils per hour, so it has to go in the top of the fraction. That means the 10 milligrams has to be in the bottom. It also makes sense since our other mass in micrograms is in the top of the rate block. We'll have to convert it in just a minute. And now come the conversions. We know that we need to be in mils per hour, so the time conversion is first. There are 60 minutes in an hour, and minutes is on the bottom for the first block. That tells us it has to be in the top for us to eliminate it for the answer. Also, we know that our drug concentration is in milligrams, but we have micrograms. Since it's in the top at our starting point, it has to go in the bottom of the conversion block to be eliminated. Now we can go through and cross out all of the units that we have accounted for. After that, we're only left with mils in the top and hours in the bottom, which is what we need for our final answer. So multiplying all the numbers across the top and then dividing by the product of the numbers on the bottom, we get the same answer as before, 30 mils per hour. The advantage for learning and using this method is, if you follow the rules, it's much easier to set up and much more difficult to get the wrong answer. Once you get used to doing it this way, it'll likely take less time than doing it piece by piece and trying to keep all of the conversions straight. Let's look at another one. For this problem, we have a 63 kilo patient on a Precedex strip at 0.4 mics per kilo per hour. Drug concentration is 4 mics per mil, and we're looking for the infusion rate in mils per hour. We already have our time in hours, so we shouldn't need a time conversion. The doses are also in micrograms. Therefore, we really don't need any conversion factors, and we can use the rate, weight, concentration form for our fraction. Plugging in the data puts 0.4 mics per kilo per hour in the first block, weight in the second block, and concentration in the third block. Again, the kilograms has to be in the top to cancel the kilograms from the rate. For the same reason, the microgram part of the drug concentration has to be in the bottom. Crossing out the units gives us mils per hour, so now we can do the actual math. Product of 0.4 and 63 in the top, divided by 4 in the bottom, giving us an answer of 6.3 mils per hour for the infusion rate. So let's think backwards for a minute and see if this still works. What if we already have the infusion rate and the weight-based dosing order, but we have to titrate up for effect? If we want to get the new order from an increase from 6.3 mils per hour to 7 mils per hour, we can use the same process. In this case, we know the new rate is 7 mils per hour, but we want to get back to mics per kilo per hour. This time we have to put weight on the bottom so that it's in the bottom for our final answer. Micrograms will go in the top, and the hours unit will stay right where it is. The only unit that will cancel is milliliters, so it'll be 7 times 4, or 28 in the top, divided by 63 now in the bottom, giving us the new dose of 0.44 mics per kilo per hour. Last problem. Let's say we have a drug that's in units like insulin or vasopressin. Do we treat this the same way as grams, milligrams, or micrograms? Yes. In this case, we put the rate of 0.03 units per minute in the first block, concentration with units in the bottom so they'll cancel, and then the time conversion to get us from minutes to hours. Crossing out units and minutes, we're left with mils per hour, for a final answer of 5.6 mils per hour. This has been a quick overview, and you have a 10-question quiz for practice. Please set up each problem as a dimensional analysis fraction and show the cancellation of each unit set in your work. This last slide has a few online resources and calculators for this type of problem. Good luck and happy converting!